I wanted to solve a problem that involves momentum conservation. And in this problem, we're thinking about a cannon mounted on a rail car. And the cannon on the rail car fires a shell. And we're going to apply momentum conservation to the problem to find out the recoil speed of the rail car when the cannon fires the shell. So this is a problem a bit like firing a bullet from a gun. If I fire a bullet from the gun, if the bullet travels, say, towards the right, then the gun, as you know, will recoil towards the left. And for the bullet in the gun, or the cannon in the shell, the understanding in terms of momentum and momentum conservation is that initially the cannon and the shell were at rest and had zero momentum, or the bullet and the gun were at rest and had zero momentum. You fire the shell, you fire the bullet, you set the bullet or the shell in motion. You also set the cannon or the gun in motion. But still, because of momentum conservation, the total momentum of the gun and the bullet, or the cannon and the shell, must be zero. So whatever momentum the bullet or the shell carries off to the right must be balanced by a momentum that the cannon or the gun carries off towards the left. And so that's going to be the principle for solving this problem. I'm going to start by making a sketch. On the sketch, here's the rail. Here's the rail car. And then here is the shell that we've fired from the rail car. So that's not a great piece of artist's work, but it's a little picture of what's going on. There's a number of quantities, a number of values that we know in this problem. We know the mass of the shell. I'm going to call the shell object number 1. So its mass is m1, and it's 1,100 kilograms. And I also know the mass of the rail car and cannon. I'm going to call that M2. And it's 36,000 kilograms. So it's much heavier than the shell. I mean, like the gun is much heavier than the bullet, the cannon rail car is much heavier than the shell. So those are the two masses we know. And then we know the velocity of the shell, and we're going to try and figure out the motion, the recoil of the rail car. So let me add the velocity of the shell. Here's, say, the initial velocity vector. And we know the magnitude of the velocity vector was 1,200 meters per second, the moment it was fired. And we know that the angle of the velocity vector was 35.4 degrees at the moment it was fired. And our job is to find this recoil velocity of the recoiling cannon and rail car. So that's really our task here. And the way we're going to do it is by applying momentum conservation. So the basic idea is that before we fire the shell, the momentum is zero. And because of momentum conservation, after we fire the shell, the total momentum of the shell and the rail car will still be zero. Despite the fact they individually have momentum, they individually are moving, their total momentum must still be zero. So I'm going to write that down. So the final momentum, I'll just call it P, will be equal to the initial momentum, I'll call it P0, and that's going to be 0. And these are the sums of the momenta of the shell and the rail car after we fired the shell, and the shell and the rail car before we fired the shell. Now, momentum is a vector, so it has a size, it has a direction. To solve this problem, because the rail car recoils along the track, we just need to consider the horizontal direction. And we don't need to worry about the vertical direction. So we're actually just going to consider the momentum conservation in the horizontal direction and not worry right now about the momentum conservation in the vertical direction. So let me just write that down to make that clear. We're going to add up the momenta of the shell and the rail car in the horizontal direction after the shell has been fired, and that would be equal to the sum of the shell and rail car's momentum before the shell is fired, and that is also 0. And now I'm just going to fill in what these momenta are before and after. So after, we've got the momentum of the shell. So momentum is mass times velocity. But we want the component of the velocity that's along the horizontal direction, because we want the component of the momentum that's in the horizontal direction. And so if you look, that component is adjacent to the angle theta. And so this is the total momentum, but we want that horizontal portion. It will be that m1 v1 multiplied by cosine of theta1. So that's the momentum of the shell, and then the momentum of the recoiling rail car, well, it's simply recoiling along the track. So it is simply its mass times its velocity, m2 v2. And all these add up to the initial momentum, and that initial momentum, because both things were at rest, is 0. And so we built a little equation from the concept of momentum conservation that contains in it the thing that we're trying to find, which is the recoil velocity. And everything else is known to us: the shell's velocity, the masses of the objects, and the direction of the shell. So let's go ahead and rearrange this equation. I'm going to move the term involving the recoil velocity onto the opposite side of the equal sign from the term involving the shell's velocity. And then I'm going to divide through by the mass of the rail car. And that will give me an equation that is the following one. The recoil velocity is in proportion to the shell's velocity and depends on the ratio of the shell's mass to the rail car's mass and the direction that the shell was fired at. And all these quantities over here on the right, we know them all. I can fill them all in. I won't write them all out, but we've got a velocity of 1100 meters per second for V1. We've got, for the ratio of the masses, we've got 1100 kilograms over 36,000 kilograms. And then we've got the cosine of 35.4 degrees. And if you put in all the numbers, you get 30 meters per second. And that is the recoil velocity of the recoiling rail car. Let me make a couple of comments about it. So the shell was traveling very fast, 1100 meters per second. By comparison, the recoiling rail car is traveling much, much slower, 30 meters per second speed. That's because the the shell was relatively light compared to the heavy rail car. And that's just like a bullet fired from a gun, right? The recoil of the gun is at a much slower speed than the speed of the bullet because the gun is heavier than the bullet. And it just depends on the ratio of the masses. Another comment is that, well, our velocity V2 that we figured out, that's negative. The velocity V1 that we put in, that was positive. That's because the recoil is in the opposite direction to the direction of the shell. And so the signs are telling us that the recoil is opposite the motion of the fired bullet or the fired shell. And finally, the equation involved this angle of the gun's barrel, the cannon's barrel, or the cannon's muzzle. It's like the pitch that the shell was fired at, or the bullet was fired at. And so the more level you fire it at, then the more the recoil in the horizontal direction. The more vertical that you fire it at, then the less recoil in the horizontal direction. And so that's another feature of the equation. Anyway, this was a problem that was simply solved by momentum conservation and is a nice example of momentum conservation. Similar examples to this are, as I mentioned, the firing of a bullet from a gun, the motion of a squid by directing water in the opposite direction, the motion of a rocket by directing fuel in the opposite direction. All of those are the same type, very similar problems.